Hello everyone, welcome back, and today we are solving Leetcode problem 840 magic squares in a grid. Let us try to understand the problem first. We are given a grid containing numbers from 1 through 15. But here is the key thing. We are only interested in a 3x3 subgrid inside this larger grid. For example, in this input there are exactly two possible 3x3 squares we can form, one starting here and another starting here. Our goal here is to count how many of these 3x3 grids are magic squares. So what is a magic square? 3x3 grid is considered a magic grid if all of the following conditions are true. It contains only numbers from 1 through 9, and each number from 1 to 9 appears exactly once. The sum of every row, every column, both diagonals is exactly 15. No duplicates, nothing missing, and all sums must match. In this example, let us look at the first 3x3 grid. Each row adds up to 15 like so. And each column adds up to 15 like so. And both the diagonals add up to 15. Perfect. This is a magic square. Now let us look at the second one. Rows, they are fine. Columns, they are also fine. Does it contain numbers from 1 to 9 exactly once? It does, but what about the diagonals? Nope, neither diagonals sum up to 15, so that one does not count. So now we want it to return 1 because only one magic grid can be formed. Let us try to discuss the brute force strategy here. So it's very simple actually. We have to check every possible 3x3 square in the grid. And how do we do that? Think of each cell as a potential top left corner of a 3x3 grid. But obviously, not every position works. We need to make sure that there are at least 2 rows below and at least 2 columns to the right. So we loop like this. Rows from 0 to rows minus 2 and columns from 0 to columns minus 2. That guarantees a valid 3x3 square every single time. So what happens at each position? Or for each starting position, we check 4 things. All values are between 1 and 9. All values are distinct. Every row sums to 15 and every column and diagonal sums to 15. If any of these checks fail, we immediately stop and move on. So in code terms, this naturally becomes one loop for rows and one loop for columns. Each row, column pair represents one candidate of 3x3 square, and that's it. We don't miss anything and we don't check anything unnecessary. So once we've picked the 3x3 square, we need to decide is this a magic square or not. That means checking, the few conditions like all the rows adding, all the columns adding, all the diagonals, and each number from 1 to 9 is appearing at least once or not. One thing that we should emphasize on is returning early. The moment we know a square is not magic, we stop checking, we move on to the next 3x3. This keeps the code clean and efficient. That's also why putting all this logic inside a helper function makes sense. It lets us just return true or false or 1 or 2, or 1 or 0 instead of dealing with breaking out of nested loops. So that is all for the logic. Now let's start coding. So I'm going to start by writing a helper function called magic, and this function will simply tell me whether the 3x3 square that we are looking at is a magic square or not. Instead of returning true or false, I'll return 1 if it is magic and 0 otherwise. That way I can directly add it to my result. So the first thing inside this function, I want to make sure that every number is between 1 and 9 and there are no duplicates. So I'll create a set called values. Now I'll loop through the 3x3 grid using 2 nested loops from R to R plus 3 and from C to C plus 3. For each cell, if the value is already in the set, we immediately return 0. If the value is not in the range of 1 to 9, we also return 0. If neither of those happen, I add the value to the set and keep going. If we successfully get through all 9 cells, that means all numbers are valid and all numbers are distinct. Next, I am going to validate the row sums. There are only 3 rows in this 3x3 grid, so I loop from R to R plus 3. For each row, I'll sum the 3 values starting from column C up to C plus 3. If any row does not sum up to 15, we immediately return 0. There is no point counting once. We know it's not magic, right? So, and now I'll do the same thing for columns. I add values at grid of r and I, and grid of r plus 1 and I, and grid r plus 2 and I. So if the sum is not 15, again I return 0 immediately. Let me finish this code. And done. And finally, now we check the two diagonals. The first diagonal goes from top left, center and bottom right. And the second diagonal goes like top right, center and bottom left. So if either of the diagonals does not sum to 15, I return 0. And finally, if none of these checks failed, that means this 3x3 grid satisfies all magic square conditions. So at the very end of the helper function, I return 1. Now outside the helper function, I initialize a variable called res to store the count of magic squares. Then I loop through the grid, rows from 0 to row minus 2 and columns from 0 to columns minus 2. Each row comma column pair is treated as the top left corner of the 3x3 grid. For each position, I simply do res equal to res plus magic of rows comma column pair. If it's magic, 1 gets added. If not, 0 gets added. Nothing changes. So the final result is after checking all possible 3x3 squares, I return res. That gives us the total number of magic squares in the grid. So even though it looks like a lot of checks, everything inside the helper function is constant work. So the overall time complexity is still big O of rows into columns. So that's all for today. Hope you enjoyed this. See you guys later. Bye bye.